So instead of doing math this week, let's try something different. This is going to be for both the MES2 and MES3 class. You see up here it says MES3, but this is also going to be for MES2. Um, I kind of want to go over how to read a wiring diagram, and I'm sure most of you have looked at a wiring diagram and tried to follow the logic and read the wiring diagram, but there's a little bit more to reading a wiring diagram, and I kind of want to go over how I look at a diagram, being that I had spent 40 years in the trade and have seen a lot of diagrams, and kind of explain the things that I see when I look at a diagram to you, and see how that relates to what you see. Many years ago, I was showing a first year apprentice some information that I was looking at on a wiring diagram, trying to explain why I was going through the steps I was doing to troubleshoot. And he looked at me and said, "That doesn't mean anything to me. I don't understand." So um, I hope this helps. And instead of doing math, maybe you'll like this a little bit better. So the assignment is going to be, there's going to be a quiz for this assignment, but the assignment is going to be to watch these videos. There's probably going to be more than one because I'm only able to do a 15-minute video at a time, and I've got to kind of keep track of time here. But probably a couple videos, and then I'll stop, put together a little quiz, and this could take more than a couple weeks, but this will be your first night of the week assignment instead of doing math. So I put a tab here for wiring diagrams, and all you'll see right now is right here where it says Bryan Triple Flex Boiler. Now, Bryan is a boiler manufacturer from Indiana. They make a boiler that's called a Triple Flex boiler. Probably between 8 to 10 years ago, this was a brand new design, brand new boiler for Bryan. I started up several of them in central Ohio area. I got pretty familiar with the wiring diagram. It was something different, than what we had seen on boilers in the past. Touchscreen display, a lot of electronics, but something that once you get familiar with, it seems to make good sense. So when you click on here, you're actually going to see there are several documents. This is the diagrams. There's actually 2 pages of what I'm going to call just a diagram because of terminology. We're going to start with that. This is the Bryan Triple Flex terminology. I will update this probably with every new video. But for now, if you click on that, you'll see some of the terminology that I wanted to go over to try and explain my thoughts about what you see when you look at a diagram. If you look at this diagram here, this looks like what you would call ladder logic or a logic diagram. And we would do this in the class if we were in person, and we could actually have you wire this up. I have electrical trainers with all this equipment on it. You can see here that the stop button is what's considered a normally closed momentary push button. That means that the spring holds this up. If you push down on it, it'll open, but normally it goes closed. And the start button is just the opposite, is a normally open momentary contact push button, which means the spring is pushing up. You have to push down in order to close it. Now, in order to get this contactor, motor 1 or motor contactor, or I should call this a motor starter, because right here is OL, which is the overload, and a motor starter is a contactor with overload. So in order to get power right here, we have to have a complete path for the current to flow, which means we push this button down and we get power here, assuming that the overload is not tripped. We have the neutral side there, and this load right here, this coil energizes and the contacts pull in. Now, when that happens, there's a set of contacts here that's associated with this coil that close. And when those close, it bypasses the start button and allows us to release the start button, let it go back to its normal position. and there's a path for current to flow so that it stays energized. Now, if you break that path by pushing down on the stop button, this will de-energize, this contact will go open, and when you release this, this will go close. But now that this is de-energized and open, you have to go back and push the start button again in order to get it to restart. That is the logic behind this. And in this particular drawing, you have multiple start buttons, 2 of them, and 1 stop button. And down on this rung of the ladder logic, you have a float switch and a temperature switch, and you have a secondary, a second motor starter. If the float switch was to make, but the temperature switch did not make, it would not energize. It has to be both of these. So because this is a series circuit of controls, both controls have to be closed before this will come on. If you put these in parallel, which would mean that the temperature switch would be down here and it would be in parallel with the float switch, then either could make this motor start. But right now it takes both because of the logic. So this is simple ladder logic, and the problem with this, or the thing about this, is that you don't typically see this on a lot of the equipment you work on nowadays, because a lot of the stuff you work on has logic controllers, like programmable logic controllers. If you hear the term PLC, and that'll probably be a quiz question, that means programmable logic controller. These are microprocessor based. Back in the early 90s, I started taking a degree program at Columbus State in electromechanical engineering, and the reason I started taking it was because they offered a class in microprocessors, and I wanted to know what microprocessors were. And then along comes DDC control, direct digital control logic. This is what we do nowadays. This is typically everything you see, from a digital wall thermostat to the circuit boards that are in every rooftop unit, and what you're going to see now with this lesson that we're going to do, a logic controller made by Honeywell that controls a Bryan boiler. And you can see on here where it talks about how ladder logic is involved in the program language. Now, I teach a class at Columbus State in ladder logic and doing this physical wiring here. But after you get through a couple of their classes doing this, then you get to program these points. And this is an input. This would be a switch input, and here's an output, which is the coil. So you actually use this type of logic, but you input that logic into a programmable logic controller with the language, and instead of having hardwired switches like this with 120 volt going through them, these basically are just inputs. And also we can do that in my classroom when we get back to in-person classes. Okay, I say I'm 8 minutes into the video now, so we got to move along. I'll go back. You can see the terminology page is still open here. Every time you open one of these, it should open in a separate window. So I want to go to the diagram page 1, and I want you to take a look at the 2 diagrams. This is diagram page 1, page 2, and what you're looking at here in the center is the Honeywell hydronic controller. It's the R7910 Sola controller, but it is the master controller for this particular boiler. I know Lochinvar uses them. I'm sure a lot of other manufacturers, Cleaver Brooks, uses this type of controller. But understanding this controller is very important. But in general, I want you to understand the diagram and how it's laid out. And when you look at this from a distance, which you're looking at now, you really can't make out any details. This looks like a ladder diagram, and it's as close as you're going to get to a ladder diagram for what we're looking at. But when you look here, all of these connection points here go into this logic controller, and the actual logic of what's going to happen is contained inside of this controller. In fact, when we get to the page 2, you'll see right here, this is the actual plug-in module. It's a little memory card that you plug in that's programmed with the logic that this controller needs to actually make it operate, and that memory card is programmed by the manufacturer, which in this case is Bryan. So let's start as you scroll down on this page 1 PowerPoint. We'll scroll down and you'll see the top of page 1. We're actually looking right up here right now. I've got several screenshots to show you. Here's some notes that are pretty important. It basically says that if you are going to be the one connecting the devices to this boiler, and I'll show you where some of those are at, it's your responsibility to connect them correctly. If you're going to replace a wire, it has to be rated at 105 degrees C and have a certain rating, and this boiler must be grounded in accordance with the code. And then over here it says EBM PAPST, EBM pass. If you was to Google that, you would find out that this is a manufacturer's name for the actual blower that's in this boiler, and it is considered a combustion air blower, or they might use the Amatec. And you can see here that the EBM version, there's a 208 60 hertz 3-phase 230 or 460. For the Amatec, it is a 208 or 230. And this table, here's some letters here that we'll need to look at. Gives us some information about the transformer wiring and gives us some information about the power and control fuses. We'll look at that in just a second. Here's the input power right here, 3-phase input power, and you'll see that there's 3 fuses, and here is the letter D, says the amp primary fuse, and that is column D right here or column D right here. If it's a 208 volt EBM PAPST, all of these fuses would be 9 amp. Same thing for the 230. Now if it was a 208 Amatec, it would be 20, and the 230 would also be 20. So that's where they're giving you this table to show, based on which blower assembly is put in. But here's the funny thing about this, and when you look at this, you may think, okay, here's 3-phase power coming in through the fuses, goes directly to this variable speed combustion air blower. But there's no motor starter, there's no contactor, there's no way to turn this blower on or off. And that looks kind of confusing. Now, obviously, there is nothing else on this boiler that has 3-phase power going to it, because right here you've got L1 and L2 going over to this step-down transformer. We'll get a little into detail about that. But the only 3-phase piece of equipment on this boiler is the actual combustion air blower, and it is fed directly with 3-phase power without a contactor. So does this fan run continuously? No, it does stop and start. So I see I'm about 13 and a half minutes into this video. I've got to finish this one up here in about a minute, and then I'll make another one. But what I went to now, I opened up the triple flex diagram page 2, and this is page 2 here, because on page 2 you'll see this connector right here, and this is very important because this is a connector that connects to that 3-phase blower motor, and that blower motor is a lot more than just a blower motor. It is a blower motor with a VFD built into it, and it controls the speed of the blower with this signal called PWM. And here is the tach, which anybody that's ever heard of a tachometer, you know that is an indicator for speed. So there's 25 volt plus, 25 volt minus, but then you have your PWM and your tach. These control wires coming off of J2 right here go to that 3-phase blower motor right here, and that is the control for that blower motor. Next video, we'll start with what PWM and what the tach